Hi, my name is Guang, 12 years old, primary 6, Ranjiva Primary School. Over here we have a continuation from the previous lesson. So for this lesson we'll be continuing to have techniques of limit calculations, and we'll be moving on with we'll be continuing on with the gamma function. Okay, so for gamma function, although we have used it before, but for gamma function over here, we need to first take note of a few things. So first of all, it is the definition of the gamma function. So the definition of the gamma function, so you can take any single letter here like Z and all, and then after that, so the definition is integral 0 from infinity e to the power of negative t x y whatsoever except for what you have chosen here, which is Z in this case. Then after that it times t to the power of z minus 1 and then dt. Okay, so over here for this part, you can choose any letter here. For this part you can choose anything except for what you chose here. So we know the definition already, right? Well, another thing is that, so I'm just going to take a different letter here, which is n. But why if I put an n plus 1? But why would I put an n plus 1, you may think? So over here, you can actually take it out, which is n. So gamma n plus 1 is n gamma n. Okay. So over here, if you keep going on, you supposedly will keep on getting it until like gamma 1 or something and all, because if you continue, it's going to be quite a problem. So for this part over here now, we are going to have a few examples like what gamma 1 is, because that, as I told you, this part will be like, it will keep on going on until gamma 1 or something like that. But what is gamma 1? Well, gamma 1, you can just sub the z in, which over here we'll have, in this case it'll be 1 minus 1, so I'm just writing this extra step, okay? So 1 minus 1, so t to the power of 0, it is basically 1, right? So as you can see here, 0 to infinity e to the power of negative t. Well, I have a negative here because over here you can have a negative here, so when you integrate it, what you will get is negative e to the power of negative t going from 0 to infinity. So as you can see here, so first of all, if it's to the power of negative infinity, because this is negative, so it will be 1 over instead. So this, what we will get is a 0. So it is technically a 0, negative 0 minus, whereas in this case it will become plus because of this negative over here. So e to the power of negative 0, which will just get a 1. So as you can see here, if you go by doing this, you'll keep on getting until you get n factorial, whereas you have, because even if you keep on doing until 1 gamma 1 is basically 1. So gamma n plus 1 is equal to n factorial. Okay. So other examples we can also put it in and all. It's just that, for example over here you can also have another example like gamma 3. So we'll be subbing it in again. So over here for this part, 3 minus 1, you get a 2. So over here you put this inside this part and you'll get and thus you can use the integral by parts over here and you'll get Whoops. So this is what you get, and in case you didn't know what this is, you can use limit. So for this part, it will be t approaches to. So as you can see, for this part, what you get over here is that, so t squared and e to the power of negative t, right? So this part, it's indeterminable, e to the power of t, because it's now in the denominator, which you'll get the indeterminable form infinity over infinity. Well, behind part over here, you can take this out and you get 2 whole integral from 0 to infinity e to the power of t. Here, well, over here you can use another integral by parts since there's still another t. So it will be like this, but if you're wondering what happens to this part, is that you can use the L'Hopital's rule, and over here, and since you put it in again, here you have a minus instead. So over here, if you're wondering how you're supposed to do this, you can use the L'Hopital's rule, whereas you get the denominator stays the same, because both sides differentiate. Well, for this part, you have another one of these, which is t times e to the power of negative t from 0 to infinity. Then after that, over here, what you have in the end is plus. So you will still have this 2 here, and then you have e to the power of negative t dt. Okay, alright, so over here, now that you have this, I'm going to continue with this part, which you'll get. So you use L'Hopital's rule once again, which will get 2 over e to the power of t. And then after that, over here for this part, what you'll get is, because once we get like the first part over here, you can easily tell what you're going to get here. So for this part, now you can integrate this, and you'll get a minus 2 e to the power of negative t from 0 to infinity. So for this part over here, as you can tell, how you can sub it in, and what you get over here on the denominator will be an infinity, while the numerator you get a 2. So here will be negative 0, and since this is practically in the same situation, so it will also be another minus 0. Well, for this part, on the other hand, you have minus 2 to the power of negative infinity. So once again, it's another minus 0, because negative infinity over here at the power. Then after that, if it's 0, it will be plus, because of the 2 minuses, as then this part was minus, so as this minuses this, the 2 minus cancels out each other. Well, over here, e to the power of negative 0, which is e to the power of 0, is equals to 1. So these 3 zeros are just practically useless, and you get a 2, which shows that this is practically correct, whereas for this part, gamma 3 is 2 factorial, which is still 2. Okay, so I'm just going to show it to you like this. Well, but there's another problem over here. But what if it's a fraction like half? So over here, just take a quick look before. So if gamma is, if it is gamma half, which you cannot use the integral by parts for, it will just continue being fraction, because no matter how big it is we wouldn't have to worry about it, but we'll have to worry about it if it is like the power is a fraction, which in this case is half. So for this part, what we have over here is, so the first step is always the same thing, whereas you have this part. So half minus 1 is negative half, and then dt. So over here what you can do is you can let u be equals to t to the power of half, okay? So over here, as u is equals to t to the power of half, dt will, du will be equals to like this, okay? And then the boundary will be, so u's boundary will still be from 0 to infinity, okay? Alright, so for this part over here, now that we have this new variable over here, u, it will be equals to from 0 to infinity. And then for this power you have is that e to the power of, so as you can see, this will become u squared. So e to the power of negative u squared, and then times, well, for this part over here, whereas there will be a negative, and for this part, if you see for this part, it will be able to cancel each other out, except for the half, obviously. So for the half for this part, it will become a 2 for it have moved to the other side. So for this part, it will be like this, okay? Alright, so what you'll get over here, now that you have reached this part, is that, so instead of like trying to do whole integral by pi and all, you simply just square root this whole thing, which means that you square it. So which means that you have to square root it. But why would I want to square it? Well, I'll show you why in a sec. So once you square it, because that this is a definite integration, so for this part, no matter what variable you use, in the end you're still going to sub it into the boundary and all. So the variable doesn't matter. So you can put these two apart and you can change the variable for here and here, which you will get 0 to infinity e to the power of, as I told you, the variable in the end is going to get subbed in, so no matter what letters you put in the end, it's still going to get subbed in. So we're going to change it. So for this part, it's practically Cartesian coordinates, whereas you change this part to dx, while you change the other part to dy. Well, what's so special about this though? It's not double integration, although there are two integration parts. Well, these are iterated integration, but we are going to change it to double integration in a sec. And there you go, we have so we have turned iterated integration to the double integration, okay? And now that we've gotten this, we can change from, so this is the Cartesian coordinate, right? So Cartesian coordinates over here, we can change it to polar coordinates, whereas it will become, so over here when it becomes a polar coordinate, it's like So this is somewhat like one of the sector over here. So for this part, how you can tell, so what is this arc? So DL, which is this length is equals to, so what is this length equals to? This arc is equals to, it is equals to RD theta from the angle from this part which you get until here. So RD theta, the radius. Then after that, for this part, what you have is dr. So in order to change it to polar coordinates, dx, dy will become RD theta and dr. Okay. So what you get over here is, so wait, later I'll write the boundary. So for this part over here, you can tell that here x and y is going to be r, d, r, and d theta. But what about what will happen to the, wait, give me a sec. But what will happen to the e? Well, for the e, as you can see for this part, you can combine these two, which you have the Pythagoras theorem and all, and you'll get negative r squared. Okay, but what about the boundaries? You may wonder, oh wait, but this boundary, can it still be 0 to infinity? Well, for r over here, it will still be from 0 to infinity, while on the other hand, for d theta, as you can see here, for dx, both dx and dy, they are all from 0 to infinity, and none of them are to negative infinity and all. So that means that the theta will be in the first quadrant, since all of them are positive. So it will be, and the first quadrant will be from 0 to pi over 2. And there we have it. And now all we have to do is to put this in and you also have another negative. So put this in, you have a half and a negative, okay? So you have a negative half over here, and e to the power of negative r squared d negative r squared, and here you have d theta. Okay? Alright, so now that you have gotten this, what we'll have is, so for this part you can integrate it already, which you'll get, whoops, I used the wrong one, and over here 0 to pi over 2, what you have is e to the power of negative r squared from 0 to infinity d theta. And as you can see for this part, what you'll get is, so for this part, if you sub this part in, it will become 0, but if you sub this part in, then it will become, so as you can see, if it minus, this negative will be cancelled, and it will be left with half integral 0 to pi over 2, and then over here the e to the power of r squared, the r squared 0, so this part will be e to the power of 0, which is 1, and this is what you get. Okay? Alright, so as for this is what you get, you can now straight up integrate it, and you get and then after that, for this, what you have is that 2 square root half pi over 2, because minus 0, it will just be minus 0. And then what you have here is that 2 square root pi over 4, so you can put the 2 in, which you will get square root pi. Okay, so as you can see here, I have shown to you first of all, the definition of the gamma function. Then after that, I have shown you the pattern for it for positive integers. Then after that, I have given to you 2 examples with positive integers, and 1 example was just a positive number over here. So for this lesson, that'll be all, and we'll have more examples for future lessons. Okay, and that'll be all. Last but not least, thank you for your watching.